the true relationship, the linear relationship between earning and education. And you have scattered plots which cannot tell that which is not a single straight line. Okay, so in that case, I'll just skip these things. So in that case, there are many factors which actually influences the which distorts and which makes the U, which is an additional term in the regression equations, heavier. Okay, so one is important, which I've already said, that the omissions of the relevant variables in the regression functions. Like in the examples, the earning is decided or determined by parental educations. Earning is dependent on the brands of the universities or the schoolings. Earning is decided by the gender. So even though you will find that there's a huge discrimination in the labor market, even in the developed countries, this gender discrimination is there, and the developing countries, this is much more pronounced. So the gender is also an important determinant of the earning potentials of the individual. So if you omit those relevant variables in the regressions, you are subject to commit certain error, and that error actually distort the linearity between the Y dependent variable and the independent variable. Apart from that, there are many other factors like the random behavior of human being, because in the social science, what we do, we deal with the human. Our subject is human beings. Okay, so and the human beings are very, very random. So you cannot just always put them in one framework, because the human mind is continuously working. So sometimes, like when you are going and seeking informations from say from a sample survey, so what happens that the enumerators are going door to door and asking for the relevant informations. The responses may be different from a same individual asked in different points of time. And why? Because sometimes the individuals are too much preoccupied with some other responsibilities and don't have so much time to exercise a lot of thinking and respond to the answer. And therefore, the responses which are reported are sometimes not exactly what the respondent is supposed to report. Okay, so sometimes these kinds of or sometimes it may happen that the respondent is in a very low mood and is not in a position to talk, and that actually influences his reporting. He's trying to get rid of the enumerators and trying to say something which will please them, and that actually also may influence your causality. Okay, so these are the factors which gets accumulated in your U term, mind it. So apart from that, imperfect specifications of the mathematical form. So when we do the regressions, we often take a linear relationship between Y and X. Okay, but many of the time Y and X are not linearly related in reality. Okay, so they are much more non-linearly related, but we fail to understand that, and therefore we don't incorporate those non-linearity in the regression exercise. And if you fail to incorporate those specifications which are correct specifications or the mathematical forms, you actually commit some errors, and that errors gets accumulated in the disturbance term. Moreover, there are other kinds of errors like the errors of aggregations, because when you do the aggregations, there are many times we just fail to notice some unobservable things. Okay, so there are many things which are not observable. So when you do aggregations, we actually missed out those informations which are very important during the aggregations. Apart from that, there are errors of measurements. Errors of measurements may come from the enumerator side, because the enumerators may be biased in certain in certain associations or for certain cause, and therefore may unconsciously influences the the respondents, and therefore it gets reflected, the bias gets reflected in the regression, in the scattered plots, where you have a very scattered values of the x and y. So all these factors actually can be categorized into the errors of emissions and the errors of observations, and these errors and omissions and the errors of observations together accumulates in the U term or the disturbance term, and we distort the linearity between y and x. So when you just take the regressions, you have to actually remember 4 set of equations. So the 2 sets of equations are from the populations, and the 2 sets of equations are from the sample. So when we start doing research, quantitative research, and take the help of regressions, before doing that, we have to conceive a model where our relevant variables are incorporated. Okay, so like the earnings and the years of education. So you are interested to know that how the earnings are influenced by the years of educations, but you are also interested to see that how is there any discrepancies or discriminations in the labor market due to gender. Okay, so in that case, you have conceived the model and you want to see these, whether that relationship exists or not. So you before running the regressions, you have conceived that as earning increases, as the years of schooling increases, the earning is supposed to rise. So there's a direct relationship between y and x. And similarly, you also have conceived that there is a adverse impact or inverse relationship in the labor market due to gender. That means the women with the same years of education are supposed to earn lesser as compared to the male counterpart. Okay, so you have conceived it in the, so you believe that in the population, y and your x will be behaving like this. Okay, so when you are conceiving this, you are expecting that the true regression line is beta naught plus beta 1 xi. So we write it expected value of yi. Why we write expected value? That means we say that on an average, y and x should be behaving like this in the population. But you know at the same time that given that there are certain limitations, you don't know many of the observed factors, you may fail to address some of the non-observables, and you may fail to incorporate some of the relevant variables, and those may get accumulated in these UI, and therefore in that your y is not actually linear, but that this linearity is distorted by the presence of this error term. Okay, so this is about the population. So now you have to consider that you cannot see the population totally, because population is beyond the reach of the researcher. It's too big for the researcher. So what you do, you try to estimate the relationship of the population through the observations of your sample. So the sample, in the sample, you have again 2 sets of relationship, which are actually this. These 2 are the relationship between in the sample. So how they are different from the population? So this UI is the error term, which is not observable in the population. So you cannot see that UI. So what you can do, you can just conceive that there is some distortion, and which can be replicated in the sample by saying that this is EI. EI is the disturbance term in the population, because UI, which is in the population, is not observable. Similarly, you don't know these beta naught and beta 1 because you haven't seen the population in totality. It's too huge. So in that case, you need to estimate these beta naught and beta 1. So you write beta naught hat and beta 1 hat. These are actually the estimated value of the regression parameters, which are beta naught and beta 1. Okay, so this is the estimated relationship where you have this EI, which is distorting the relationship between Y and X. Okay, so this is from the sample. But in the regressions, what you expect that on an average, even though there is a disturbance term, but on an average, y should be behaved like this. That means expected value of yi, which we called it yi hat, which is on an average, the y value is equal to beta naught hat plus beta 1 hat xi. Right? So you are assuming that on an average expected value of EI is equal to 0. And this error terms is measured by taking yi minus yi hat. What is your yi? Yi is the observed value of y, and yi hat is the estimated value. This is the estimated value. So if you deduct this from this equation, you actually get EI. So this is observed minus expected. So now what you do is suppose these are all your scattered points, which you get from your sample observations. And from these scattered points, you are supposed to construct the best fitted line or your regression line. So the line here, you claim that this is my regression line, or this is the best fitted line of all these scattered observations. Okay. So if you have to construct this line, what you need to do, that some of you might just recall your knowledge of straight line. So when you say y is equal to mx plus c, what does it mean? It means that m is the slope of the line, y is equal to mx plus c is the equation of a straight line. So m is the slope of the line, but if you put x equal to 0, then y value is equal to c. So c is the intercept of the straight line. So if you know these two things, one is the slope, another is the intercept. If you know these two things, you can actually construct an unique straight line. Okay. So if the value of the m is known to you, and if the intercept is known to you, you actually can construct an unique line, and this line cannot be considered. This line is to be considered unique. Why? Because it should not be overlapping with any other lines with the different values of your m and c. Okay, so in that case, we say that this line is the best fitted line. That means yi hat is equal to, say, beta naught plus beta 1 hat, beta naught hat plus beta 1 hat xi. Right? Now this beta naught is the intercept. If you put xi is equal to 0, then yi is equal to beta naught. So this beta naught is just like the c, y is equal to mx plus c. So this is the intercept term. It says that if your x is equal to 0, the value of the y, which is your, just extend it, this is the value of the y when your x value is equal to 0. And the slope is basically, if you extend the line, the slope is basically the angle which it makes from the positive direction of the x-axis. Okay, so this is your beta 1. Once you know these two values, you can actually claim a line which is a unique line, and you can claim it as the best fitted line or the regression line. So in the next step is to estimate this beta naught and beta 1. Okay, so you can imagine that you have some scattered points, and the researcher is saying that this is the line which is the best fitted line, but somebody else is challenging him or her and saying, no, this is the best fitted line of this scattered point. Somebody else further challenges and say, no, this is the line which is the best fitted line. So anybody can challenge the others by saying that, no, this is a different line, this is the unique best fitted line. So in that case, there should be some principle based on which you can derive the best fitted line, and so that nobody can challenge that best fitted line or your regression line. So what we do is basically we use this principle of ordinary least square method. So what is this principle of ordinary least square method? We actually take the error term, which is your EI, which we have already explained that it is the observed minus expected value. So we take these EI and you try to minimize these EI. So how you do that? See, suppose these are your scattered points. These points which you can see, these are your scattered points. And sorry. So this is your y hat is equal to beta naught hat plus beta 1 hat xi. This is suppose your regression line. Okay. So if it is at your regression line and these are your scattered points, what you do in constructing the regression line is you take this distance. So this distance is what? This is your E2. This distance is your E2. How you arrive at? Take the x2, which is your known value of x, and that x value will give you two values of y. What is that two values? One is that from the point itself, you get the observed value of y, which is, you can call it y2. And from the line, from the best fitted line, you get another value of y, which is your y2 hat. So the difference between the observed minus expected, that means y2 minus y2 hat, is the distance. This is the distance which is your E2, which is the error which you committed between the observed and the expected for a given value of x2. You can repeat this for, say, x3. So given x3, you see that this is your observed y3. But what is your y3 hat? You have to get the value from these, from the best fitted line. So this is your y3 hat. And the distance between y3 minus y3 hat is your E3. So this way you can generate all the error terms corresponding to all your x. And what you do in the regression is basically you try to minimize all these errors. Now, when you are taking the sum of all these error terms, you see that some are lying, some scattered points are lying below, some scattered points are lying above the above. So when you take the sum of all these distances, given that some are lying above, some are lying below, some will be positive, some will be negative. So when you take the sum of all these, some will be cancelling out, and therefore you may not get the relevant magnitude of your error. So what you do in order to solve these is basically you take each of your E1, E2, E3, E4, and this way En, and you take the square of this. So if you take square, the minus becomes plus. So minus 2 becomes 4 and 2 also becomes 4. So you take the sum of the squares of the error term. Once you take the sum of the squares of the error term and take the total, you get a concept called the residual sum of square, or which is called the RSS. And the regression is basically is derived regression line by actually minimizing these residual sum of squares with respect to these unknown parameters, beta naught hat and beta 1 hat. I'm not going to the technicalities here, but I'm saying that by just taking the minimization exercise of these RSS, you can actually construct two normal equations. And from the two normal equations, you can calculate these beta naught hat and beta 1 hat. And the formula for these beta 1 hat is this one, which says that this is the numerator is the covariance of xy and the denominator is nothing but the variance of x if you just divide both sides by n. Okay, so it is the beta 1 hat is once derived, you can actually calculate beta naught hat, which is nothing but y bar minus beta 1 hat x. Now, what you have done is you have calculated beta naught hat and beta 1 hat. These are the two regression coefficients. Now, once you have calculated, then your regression line, your best fitted line or the regression line is constructed. This you can claim as a unique line, which is your regression line or the best fitted line, which captures the relationship between y and x. Okay, how the relationship is captured. Now you have to basically interpret these two regression coefficients. Okay, so when you put xi equal to 0, this term will be something multiplied by 0 is 0. So this term will be disappearing. So once this disappears, what is left? Yi hat is equal to beta naught hat. That means when xi is equal to 0, the autonomous value of yi on an average is beta naught hat, right? And what is your what is your beta 1 hat? Beta 1 hat is nothing but if you just take the rate of change of y with respect to x, that is basically your beta 1 hat. That means if you increase or if you decrease xi by 1 unit in a discrete sense, it's a derivative, but I'm just telling you in discrete sense for your understanding that if you allow 1 unit increase in say xi, the rate of change of yi with respect to x on an average is your beta 1 hat. Mind it, in the regressions, we always talk about the association between y and x in the mean value. That means it is always an average value. It's not the actual one. Okay, so beta 1 hat basically tells you the average rate of change of the dependent variable y due to the change of the independent variable. Okay, so now I'll just go to suppose this is your regression equation. So you have derived the beta naught hat, which is 1.67, and beta 1 hat, which is 1.50. So what you get is the regression equation, which is 1.67 plus 1.50 xi. Okay, so these two, once these beta naught and beta 1 hat are estimated, you actually claimed an unique line as your regression line. Okay, so what does it, how you interpret it now? You can say that if your xi is equal to 0, the average value of yi is basically 1.67. If you just now allow xi to change by 1 unit, so the average rate of change of y, which is your dependent variable, due to the change in x is 1.50. Okay, so that is how you interpret your y, your two regression coefficients. Now, I'll just show you, there are various assumptions which are very important, but given that there is a lack of time, so I'll not just spend time on these assumptions. The slides is shared with you, so you can always go through this and go further to the books if you are interested. So I'll just show you some stata output, regression output in order to make you understand what we actually do in the regression. Okay. So I'll come back again. So let us do one more thing and then I'll go to the regression output, stata outputs. Yes. Yes. 2 or 3 things are required. So first is this one. So apart from this regression, so let us do this one first and then I'll do this one. So apart from now you have estimated your beta naught and beta 1. Now, once you estimated, so you claimed that this is the best fitted line or your regression line. Now the thing is that since you are saying that you have estimated, you have to statistically validate your estimation so that your regression equation is a robust equation. Okay, so statistically validating means you have to basically look at the statistical significance of the coefficients, regression coefficients. Okay, so for the statistical significance of the regression coefficients, what we do first, you estimate these beta naught hat and beta 1 hat. You also have to estimate the standard error of beta naught hat and beta 1 hat. These are standard errors are nothing but the standard deviation when you are dealing with a sample observations. Okay, So the beta naught hat and beta 1 hat, I've already explained how you have derived. Similarly, you can also derive the standard deviation of beta naught hat and standard deviation of beta 1 hat. Once they are derived, then you basically can construct the T statistics. So the T statistics is nothing but the estimated value minus the, observed minus expected divided by the standard error of beta 1 hat. Okay, so the T values, once you are done, you are basically, you have to do with the hypothesis testing. So what you do in the hypothesis testing, in the null hypothesis, what you do is you just put beta naught equal to 0, and in the alternative you say that beta naught not equal to 0. Same is for the beta 1 coefficient as well. So when you say beta 1 equal to 0, and in the alternative you say beta 1 hat not equal to 0, what does that mean? Just recall that equation, regression equation, yi hat is equal to beta naught hat plus beta 1 hat xi. Okay, so if you say beta 1 is equal to 0 in the population, what does it mean? That y and x are not related, because something multiplied by xi, something, if beta 1 is equal to 0, 0 multiplied by xi is always 0, so that part will disappear. So what does it mean? That xi as an explanatory variable fails to explain the variability of y, right? So y and x are not causally related. So that is basically the essence of these null hypothesis, that once you put beta 1 equal to 0, you actually claims that y and x are not causally related. But what you do it through the alternative hypothesis, you actually refute the claim or which you have done in the null. So you say that beta 1 hat not equal to 0. Okay, so your objective is basically, as a researcher, you need to reject the null hypothesis. That means your T statistics, whatever you calculate through your T statistics, that has to be statistically significant, so that you reject your null hypothesis. Okay, so because once you reject the null hypothesis, then basically your alternative holds true, right? So what does it mean? It means beta 1 hat not equal to 0. Whatever you have estimated is statistically validated. Okay, so in the regression, what you actually do in the hypothesis testing, is it clear to all of you? I'm just running very fast, and I can't help, because the time is very, very limited, and this is a huge exercise. Okay, so I'll just flag the main bullets, but if you are interested, the slides will be with you. You can always go through that and consult some good books which will help you to extend your knowledge. Okay, but I'll just flag the main issues which are pertinent in understanding regression. Okay, so your main objective as a researcher is therefore to reject the null hypothesis, and therefore you can accept the alternative, because you've already estimated some betas. If you have to accept the null hypothesis, what does it mean? It means that x and y are not causally related. So x as an explanatory variable to explain the variability of y is failed, okay, because now they are not statistically significant. So if you need to do that, you have to basically go by taking the T values. And for this T value, it is nothing but you just set, it is the estimated value minus the observed value divided by the standard error. So that this one is equal to 0. So you just put this equal to 0. So it is the estimated value divided by the standard error is your T value with that n-2 degrees of freedom. Now I'll show you this. This is basically your T distribution. This is the probability distribution, T distribution. What you do through the hypothesis testing. If your P value, so your P value is in the x-axis. It can be positive value, it can be negative values, okay? And your critical region, suppose your level of significance alpha is equal to 5%. So 5% means that you are rejecting the null hypothesis at 5% level of significance, which means that the critical region on which your null hypothesis gets rejected is only 5%. And given that your distribution is a symmetric distribution, so your critical region lies in the both sides of the tail of the T distribution. So you can see this shaded region is one side in the right hand side, and the shaded region in the left hand side together constitute 5%. So 2.5% here, 2.5% here. Okay. Now, for the rejection of the null hypothesis, what you need to have a very high value of T. So if your T value is close to 0, you are in the acceptance region. So you cannot reject your null hypothesis. So in order to, as I said, that our objective as a researcher is to get our estimation, our regression output to be statistically significant so that you can reject the null hypothesis. Okay, so how you can do that? You need to have a big value of T, high value of T, so that it lies in the critical region. The critical region is also called the region of rejection. Okay, so if it lies here in the tail, this side or this side, that means T value should be big in absolute sense, not in the actual sense, because negative value, the higher the negative value, smaller the value is. Right? But we are not interested in the actual value. We are interested in the absolute value. So if your T value is very high, it is more and more chance that it will be lying in the rejection region, and therefore you can reject your null hypothesis. Okay. So what you do is a rule of thumb. So we generally use a rule of thumb. What is the rule of thumb? As we know, on principle, we need to have a high value of T to reject our null hypothesis. Okay, so the high value of T is how much high? So that is basically, you have to remember the rule of thumb. The rule of thumb is that if your tabulated value of T, that means, if your actual value of T, which you have calculated through this formula, T value is beta 1 hat by standard error of beta 1 hat, or T value of beta naught hat is beta naught hat divided by the standard error of beta 1 hat. So if this T value is greater than 3 in absolute sense, it can be minus, it can be plus, but in absolute sense, if your T value is greater than 3, you don't go to the T table and look and go for the degrees of freedom and then find out the T tabulated value of T and then compare the actual T statistics and then conclude whether to accept or reject the null hypothesis. That exercise need not be done. Okay. Just you have to remember the rule of thumb. If your T value is greater than 3, you can reject the null hypothesis at 1% level of significance. If your T value is greater than 2, if your degrees of freedom is more than 20, which is obviously in any quantitative research, which will be always there. So in that case, you can reject your null hypothesis at 5% level of significance. Okay, so this is the rule of thumb. Once you understand, then we'll go back to the stata table. It is much easier for you now to interpret the stata output. Now we will do one more thing before going to the stata table. So we'll try to understand the 3 sums of square. There are 3 concepts of the sum of squares. One is called the residual sum of squares, which we have already done when we tried to estimate these beta naught hat and beta 1 hat, which is your residual sum of squares is equal to yi hat minus yi minus yi hat, observed minus expected. Okay, but apart from that, there are other 2 sums of square. One is the total sum of squares, and how you define this total sum of square, it is yi minus y bar, and if you take the square summation and the squares of this, you get the total sum of squares. So yi for each observations, or if each of your n observations of y, you just take the deviation from its mean. So y1 minus y bar, y2 minus y bar, this way yn minus y bar. And then you take the squares of the deviation and then take the sum, you get the total sum of squares. Another term is called the explained sum of squares. So ESS. So ESS is basically yi hat minus y bar. Y bar is basically the mean of the y observations, and yi hat is the estimated value of the y observations. So in that case, if you take these deviation and then take the squares and take the sum of that, you get the explained sum of squares, and which is this one. So what we can see, so you have three squares, concepts of the sum of the squares. One is the total sum of squares, another is the explained sum of squares, and third one is the residual sum of squares. And it can be shown mathematically that this total sum of square is the sum of the residual sum of squares and the explained sum of squares. And once you have this, if you divide both sides by TSS, what you get is that 1 is equal to RSS by TSS plus ESS by TSS. Okay. Now you see that you are interested for this ESS by TSS. And what is this ESS by TSS? It is actually 1 minus RSS by TSS. And this ESS by TSS, if you multiply into 100, it actually says that out of the total variation of your dependent variable or your Y variable, the part of the variable, excuse me, just let me take a little bit of water. So the part of the variation which is explained by x, which is your explanatory variable, is ESS by TSS. So it is also called the coefficient of determination, and it is represented by capital R square or small r square, whichever way. Different books have used different notations. So this ESS by TSS is also called the goodness of fit. So this, when you run the regressions, you also look at this R squared, because this R squared tells you that how much of the variability of your Y is actually explained by regression. So if it is said your R squared is, or your ESS by TSS is say 0.88. So 0.88 means what? That 80, if you multiply it by 100, it is 88%. So out of the total variability of Y, 88% of the total variability of Y is actually explained by the regression equation. That means is actually explained by the independent variable X, or the explanatory variable X. Okay. So R squared is the goodness of it. So what we have done so far is, let me just summarize. Yes. So we try to explain 4 different kinds of equations. The first 2 are from the population, and the next 2 equations are from the sample. So this is basically this one. Sorry. Which one? This one is actually your regression equations. And once you understand that these equations, that means if you know the value of your estimated value of your beta naught hat and beta 1 hat, you can actually claim the best fitted line from your sample observations, which is your regression line. And once you, so you need to estimate these beta naught hat and beta 1 hat. So the beta naught hat and beta 1 hat are derived by using these 2 formulas. This one is the covariance of xy divided by variance of x, and beta naught hat is y bar minus beta 1 hat x bar. So once you derive estimate beta 1 hat, you can easily substitute this beta 1 hat here. And since your y and x observations are known to you, you can actually calculate y bar and x bar. So substitute these values, you will get the beta naught hat. Apart from that, you also have to calculate the standard error of beta 1 hat and beta naught hat. And once you are done, you have estimated the regression coefficient. Now you have to statistically validate your regression estimates. Okay, so the statistical validity, for that you have to construct the null hypothesis which says that beta naught hat equal to 0, and the now for the other one beta 1 hat is equal to 0, and your alternatives are beta naught hat not equal to 0. Similarly, for the other regression slope coefficient beta 1 hat not equal to 0, and then you construct the corresponding t values. This is basically the estimated parameter divided by the standard error of beta naught hat. And these t values, as a researcher, your aim is to get the statistical significance of the estimation. Okay, so you need to ensure that your t values are as high as possible. So if the t values are low, then basically it implies that your t statistics is lying in the acceptance region, where you will have no way but to accept your null hypothesis. And if you accept your null hypothesis, then your entire estimation exercise is a futile exercise. So your aim is to reject your null hypothesis, and therefore you can claim that these estimations are statistically significant. Okay, so this is the a job which you have to do. Apart from that, in the regression, you have to also see these R squared. That means once you have done the regression, you need to see that the overall, how is the goodness of the fit of the model which you have constructed in order to understand the causality. So this R squared value will tell you that greater the percentage of the variation of your dependent variable y, which is actually captured by the explanatory variable. Okay, so now we'll go to the stata output. And so look at this one. So this is basically the regression equations. Yeah. This is actually the regression equations which we have discussed. That means you have the earnings as a function of the years of schooling. It's a bivariate analysis. Earning is your dependent variable and years of schooling is your X, or the independent variable. Okay, so you just regress earning with respect to S is the years of schooling. S is the variable which is the years of schooling. So look at the lower part, the bottom part of this state output. So what you find is that this is your earnings, and this earnings is regressed with respect to two parameter values. What are these? One is beta naught, which is your autonomous earning, even if your years of schooling is equal to 0. Okay, if you put X equal to 0, just 1 minute. Hello. हाँ, बहुत अच्छा. Okay, so if you put y is equal to what I'm saying, if you put X equal to 0, then if somebody is illiterate, no years of schooling, in that case also the person is supposed to earn something, right? So that earning, they can be through begging, it can be through through these savings, but some earnings is to be made. So that is actually your beta naught. And what is your beta 1? Beta 1 is a coefficient of the years of schooling. Okay, so which is the coefficient of your X. So your first, see the second column, the coefficient which will give you these estimates of your beta naught and beta 1. Right? So this is the constant is your beta naught, and the S is the variable for the X, or your years of schooling. So this coefficient, you see that the coefficient, this value is negative. What does it imply? It implies somebody with a 0 years of schooling is earnings negative, means earning is through borrowing or through begging or whatever way you want to interpret. Okay, so and this S is the basically your beta 1 hat, and that is saying that if you increase the years of schooling by 1 unit, your earning is supposed to increase by $1.07. Okay, so this is your regression coefficients with respect to X, right? And then this column is giving you the standard errors. So the standard errors are important because you need to understand whether your estimated values are statistically significant or not. That means in order to construct the t values, you need these standard errors, right? So what is your t value? You can easily check that if you divide the coefficient with the corresponding standard error, you get the t values. Okay, so this divided by this will give you 8.102. This divided by this will give you minus 0.764. Okay, now look at the t values and tell me that whether they are statistically significant or not. So that means you have a null hypothesis beta not equal to 0 against the alternative hypothesis beta not equal to 0. For the intercept term and for the slope term, you have the null hypothesis beta 1 hat equal to 0, alternative hypothesis beta 1 not equal to 0. Okay, so your objective is to reject the null hypothesis so that you can say that the association between the years of schooling and the earning exists. So that means years of schooling can explain a significant variation of the earnings of the individuals. So now look at the t values. So what you find for the schooling, years of schooling, the t value is 8.102. What does it mean? It means it is greater than 3. So you can say that it is highly significant. So that means you reject your null hypothesis at 1% level of significance. Just use the rule of thumb. It is greater than 3. But what about this constant? This one is 0.764 minus 0.764, which is less than 2. So you cannot reject the null hypothesis here. So although the years of schooling is significant, but this constant term is non-significant. And it happens in the cross-sectional data, especially in the when you do the bivariate analysis, because you have actually failed to incorporate many of the relevant variables which explains the earnings of the individuals, and that actually distorts the result. Okay, so the constant terms insignificant, you don't have to be bothered, but your main variable, which is your X, the years of schooling, is statistically highly significant. Okay, so the value is 8. You can cross check this t value by the p value. So this p value should be, so the rule is that higher the t value and lower the p value. So these two are analogous. If you have high t values, your p value will be close to 0. Okay, and if you have low t values, your p value will be high. Okay, so p value can't be more than 1. It's a probability value, and less than it cannot be negative 0 to 1 values, but more higher the p values, you may understand your t value will be low and it is statistically insignificant. That means your t statistics is lying in the acceptance region. Okay, so you can see that here you are rejecting your null hypothesis, you are accepting your null hypothesis for the constant term, that means beta naught term, and that can be also cross-checked from the p-values, because your p-value is 44%. Okay, so the high p-value, it is not clearly, your p-value ideally should be less than 0.05, that means 5%, less than 5%. P less than alpha is actually establishes the statistical significance. So you can check from this, you can check from the P value itself. So your P, the rule of the thumb is that your P value should be, for the statistical significance, your P value will be close to 0. Look at this one. This one is close 0. And this one is 8.102, which is pretty high, which means that it is statistically significant. This T value is low, it is low, lesser than 2, and which also is established by the high P value, 44%. Okay, so you can check both the T and the P value to statistically validate your estimation exercise. Because if your regression are not statistically significant, even though you spend time and developed your model and want to discuss your result, those results are not validated. Okay, so these results are not valid because they are not statistically significant. So the variables which are statistically significant are only those variables which needs discussions. If the variables are not statistically significant, mind it, you should drop those discussions on those variables, because they are not statistically significant, means they are not relevant in explaining the variability of Y. Okay. Apart from that, I haven't done the ANOVA here because of the lack of time, so I can't explain this part, but this part let us explain. You have one R squared. This one we have explained. So this R square is basically the coefficient of determination, or it is also called the it is also called the goodness of fit of the model. But here your R square is only 10%, okay, 10.3%, okay. So which basically says that only 10% of the variability of earning is captured by the years of schooling. And that is quite obvious, because schooling is important, years of education is important in explaining the earning, but earning is also decided by many factors. Given that we have to start from the very simple thing and then move on to the complex exercise, the multivariate things comes after the two variable or bivariate analysis. And let me just show you this model. Here, what we have done is basically, apart from the years of schooling, we also have taken this variable is actually stands for the test scores, or the which stands for the cognitive ability. Okay, so this cognitive ability, or the which is assessed through the test scores secured in the last examinations appeared by the candidates. So that actually also is an important determinant of earning, because you may have a higher number of years of schooling, but the years of schoolings are with a bad test scores. Okay, so bad test scores means that you won't be considered as an important or as a very good candidate in the job market. Okay, so in that case, these ASVABC is the average test scores from the which is taken as one additional explanatory variable. So your model now becomes, is this part visible to you? I don't know how to remove this part. I don't know. So here now earning is equal to beta naught plus beta 1 years of schooling plus beta 2 into ASVARC, which stands for the cognitive ability of the individuals. Okay, so you are moving from the bivariate analysis to a multivariate analysis, because you now have earning is actually explained by two explanatory variables. So you have more than one explanatory variable, means you are in the framework of multivariate analysis. Okay, so you have more than one explanatory variable. So you have two explanatory variables. So the coefficient, you have three coefficients. One is for the beta naught, which is basically the autonomous earning when you put both the years of education and the cognitive ability equal to 0, then the somebody who is potentially can earn is this amount. And you can see that this is negative, which means that the earning is in negative. It is done by borrowing or something like that. Okay, so and these two coefficients are basically, the first one is for the years of schooling and the second one is for the cognitive ability or the test scores which are given in the last examinations which appeared. And then you have the third column, you have the standard error. The corresponding standard error of schooling is this one, years of schooling, corresponding standard errors of the test score is this one, and for the constant term is this one. And then you have the t value. This t value is obtained by the coefficient divided by the standard error. So you can see this coefficient divided by the standard error, and you look at these t values. So what do you find? And you recall the rule of thumb. If it is greater than 2, you can assure that your estimation is statistically significant at 5% level of significance. Look at the constant term. So it is statistically significant, right? Because it is greater than 2, and you can check the p-value. P-value is less than 5%, okay? So it is statistically significant at 5% level of significance. Look at the t-values of the other two regression coefficients, the schooling and the test score, all are greater than 2. This one is 4.601 and this one is 3.598. So obviously they are significant, statistically significant, and they are at 1% level, and which you can check the p-values. P-values are all 0, right? So they are statistically significant at 1% level of significance. So the model is improved as compared to the earlier bivariate model because the earlier model you have failed to incorporate some important relevant explanatory variables. Here you have taken these by incorporating these additional variables, which is very relevant in deciding earnings, has actually improved your regression result. Okay, it's because all the parameters are now, regression parameters are statistically significant. Now you look at the R squared terms. So your R squared is still low, it is 12%, but it has improved from the earlier one. Okay, so in the cross-sectional data, actually R square is not very much useful measure of the goodness of it. Although we see R square, but we don't consider it as a very important indicator. It does indicate some useful information, but it in the cross-sectional studies, and especially in the survey research, your R square is not very, many of the times it is not very high. But there is another two concepts. I will just introduce these two concepts and I will finish over here. This is basically, one concept is called the adjusted R square that I'll explain little later. Another one is the F value. So when we interpret the regressions, we also look at these two important information, because this F value obviously gives you much better picture of the overall significance of the model. And so although we look at the R square, but we take the F value much more seriously. And for the significance, overall significance of the model, that means how well you have conceived your model. That means the explanatory variables which you have taken in order to explain the outcome variable or your dependent variable, how relevant they are on an average overall. Okay, so that is actually captured by these F value. Okay, and you see the F value is 39.98, and these two values are the degrees of freedom of the numerator, degrees of freedom of the denominator, and this F value is basically the ratio of the two two mean sum of squares, which I'm just leaving because there is not much time. So here, from here, this mean sum of squares, if we divide this one with this one, we get the F value. Okay, so there is F value, whether they are significant or not, is you don't have to look at the F table. That is not required. The trick is that you look at this probability greater than F, and ideally it should be less than 5%. Okay, so if it is more than 5%, then the overall significance of the model is not good. Okay, so it is, you see that this is 0, which means it is highly significant. Okay, so the apart from looking at the R square is important, but more important is your F value. And in order to understand whether the overall significance of the model is there statistically, in order to validate that, you look at the F value and look at this probability greater than F. And if it is, your rule of thumb is that this should be close to 0. And this should be, for the overall significance, it should be less than 0.05. Okay, 5%. Okay. Now let us go to the, I think I don't have time, so I'll just I'll share one more slide. Can you see the slide? Can you see my slides?
Yes, ma'am. Yes,
hello?
It's visible.
Okay. So I'll introduce one more concept, which is called the adjusted R square. 1 minute. Okay, I'll just put it in the full screen mode. Yes. So you recall that, so in the multiple regression, so that multiple regression is just simple extension of the bivariate regression. So the two variable or the simple regressions which we have learned, the basic principles are well understood through the two variable regressions. And when we do multiple regressions, we basically incorporate more and more explanatory variable in order to understand the variability of your Y. Okay. Now, when you are in the multiple regression framework, you also try to see in the regression output, you also try to see the adjusted R square. So what is this adjusted R square? So R square, you remember that it is ESS by TSS, or you can also write 1 minus RSS by TSS. That is your R square. Now you see that this R square is something which is important. It talks about the overall goodness of the fit of the model. But if you increase the explanatory variable, your R square will always increase. But increasing the explanatory variable is not something which is the only answer. Obviously, if you increase explanatory variable, your explanatory power of the regression will increase. But mind it, when you increase the explanatory variable, you are simultaneously compromising with the degrees of freedom. So there will be loss of degrees of freedom as more and more explanatory variables are incorporated in the regression model. So just blindly increasing the explanatory variable is not the answer. Okay, so for that, what we do, we actually see the adjusted R square. So this adjusted R square is also written in many books as R bar square. Okay, see, this R bar squares actually takes care of the improvement in the explanatory power due to the incorporation of newer and more explanatory variables, but it also take into account of the loss of degrees of freedom. Okay, so the difference between R square and R bar square is that R square, if you increase explanatory variable, your R square will always increase. But as a researcher, you know that as you increase the explanatory variable, your explanatory power increases, but you are losing the degrees of freedom. And if you lose your degrees of freedom, in that case, your overall goodness of the fit will be affected. So in that case, you have to see that whether on in totality, the overall the explanatory power is improved through the incorporation of newer variables. Okay, so the adjusted R square takes into account of both these increase in the explanatory power and the loss of the degrees of freedom. And the formula is very simple. It is 1 minus R squared. This R squared is the simple R square, which is ESS by TSS, coefficient of determination. And then you have n minus 1 divided by n minus k minus 1. So what is n? N is nothing but the sample size. And what is k? K is basically the number of explanatory variable. So if you have 3 explanatory variable, then in that case, and 100 observations, then in that case, it is your numerator is 100 minus 1, and in the denominator, it will be 100 minus 3 minus 1. Okay, so what is what you get through the R bar square is that, look at these expression. So if you increase one explanatory variable, what will happen to your R square? This R square will always rise, right? Because R square is always increasing in the explanatory variable. So your R square will rise. And if you keep this constant, what happens to 1 minus R square? So if R square increases from say 0.75 to 0.80, so what will happen to 1 minus R square? It will fall. So something you are deducting from 1, which is reduced. So what happens to your R bar square? It will rise. So R bar square will rise. There is a tendency for increase in R bar square due to the increase in R square, and that is basically because of the increase in more and more increase in your X, or the explanatory variable. So if you increase more explanatory variable, the explanatory power of the regression increases, and that has a positive bearing on R bar square. But at the same time, if you just keep this constant for the time being and just see these fraction. So if the number of explanatory variable increases, then what happens to your denominator? So K is your number of explanatory variables. Suppose your number of explanatory variable was 3. So it is n minus 4, right? 3 minus 1, n minus 4. Now your explanatory variable is 5. So it is n minus 6, right? So in that case, if you're 100 minus 6, which is 94, initially it was 100 minus 4, which is 96. So something in the denominator is getting smaller. So denominator getting smaller means what? That the fraction is increasing, right? So if you 100 divided by 5 is 20, but 100 divided by 20 is 5, right? So if your denominator gets heavier, the fractional value gets smaller. So if the value gets smaller, then what happens? 1 minus something, which is constant, suppose, into something which is smaller, which is sorry, what happens? It is become which is bigger. Because the denominator is smaller, this becomes bigger. So what happens? You are deducting something bigger value from 1, right? So in that case, R bar square is supposed to fall. So R bar square is increasing because the explanatory power increases with the increase in X, number of explanatory variable, but R bar square has a tendency to fall because there is a loss of degrees of freedom. So overall, what will happen to R bar square, you actually don't know. So R bar square may rise, R bar square may fall. So the overall goodness of the fit is actually measured by R bar square rather than R square. So I'll stop here, and I think that this is basically the F value. F and R's are also related, and therefore if your overall goodness of the fit is increased by increasing your R square. Okay. but there is a r square in the denominator, and it is also adjusted by the degrees of freedom. So I'll just end here because there is many things to be explained, and the time is not much. So if you have any question, I would love to address those questions. Any question, please?
Ma'am, may I ask the question?
Please.
Yeah, ma'am, it is actually basically very basic question, but many times I find this problem. That's why I'm asking.
Yeah,
This is
your
Dr.
name and
yeah.
Can you please tell me your background?
Yes, ma'am. Yes, ma'am. I'm Dr. Radha Vyas from Surat, and I'm faculty in management. Okay. And my area basically is finance and entrepreneurship.
Thank you. Thank you. Nice to meet you.
Yeah, thank you, ma'am. Ma'am, first of all, you explain very simple way in a very lucid manner, because I attended earlier also some workshops, but regression, something very difficult, statistical, some fundamentals and phenomena. So you explain in a very simple way. So today I think I even clear many of my doubts also during your session itself. Now my basic question is, yes, ma'am, my basic question is that first normally we do correlation, and if we find any association, then we try to measure the strength of the association through regression. Am I right?
No, strength of the association is measured through correlation coefficients, but strength is not something which is actually establish the causality, because correlation gives you only that there is an association, but which one is impacting what, that you can't say. So if you can't say that whether X is impacting Y or Y is impacting X, because correlation coefficient is symmetric. So correlation coefficient of XY is exactly equal to correlation coefficient of Y and X. Okay.
Yes, ma'am. So my question actually is regarding linearity. So my point is that whenever I do some real research, I write the paper. So is it necessary, compulsory that first of all, I'm supposed to check the linear or non-linear relation, then only I can use this regression, or there is nothing like that?
No, not at all. Since I started with the bivariate analysis, I thought of just starting from the scatter diagram, because scatter diagram is a point through which we develop these line of best fit. Okay, so and then I thought that I must explain little bit about correlation coefficient, because otherwise many of you are having these doubts that if correlation coefficient can do the strength of the associations and many things, then what is the need for the regression? So in order to understand the strength of the regressions or the scope of the regressions, you need to understand the limitations of correlation coefficient. So that's why I explained that. But you need not have to do all these steps together. You can start with the scattered plots and try to understand whether there is some pattern of association exists, and then you can conceive your modeled regression models and run regression.
Okay. Now my second question, I think in the practical output, which you explained lastly with the result, so you apply, I think, Strata software, if I'm not wrong.
Yes.
Okay. So ma'am, is there any difference if I do the same thing on SPSS?
No, not at all. So whichever software you are comfortable, you can do that.
Okay. So it is not necessary to use specific.
No, it is. See, many of the advanced things which we do, some of the softwares may give you much better results. So that is much advanced level. But for the basic things, it is, you can do either through SPSS or Strata, whichever you feel comfortable.
Okay, ma'am. Ma'am, last question. Same technique is also there, structural equation modeling. So is it like that if I write paper and I wanted to publish in a good journal, so they always expect such kind of advanced analysis or multivariate regression is fine?
See, that is absolutely beyond my scope of,
Okay, ma'am. No problem. Thank you, ma'am.
Which journal you are talking, which subject you are talking.
Yeah, I understand. Yeah, I totally understand.
You are talking, I have no clue. So it depends upon the current trend. So you have to consult some good journals and see what is the trend and what type of research is going on. So, and that will actually compel you to take the methodology, right? I can't which one is the best.
No, I got the answer, ma'am. Thank you. Thank you very much.
Thanks a lot.
Actually, I will request here to all the participants to confine yourself within the topics discussed, because too much generalized questions will make the resource person confused, because all the resource persons are specialized in certain areas, and ma'am is so busy in spite of her very busy schedule. She has been agreed to join us with a very valuable lecture.
So it's my pleasure as well, because I also try to understand how much I know. If I fail to explain things in a mixed crowd, that basically questions my ability, my understanding on the topic, because I should be able to understand the able to explain things at the very basic levels, so that I can reach everybody. If I understand
So
something
this is the
better.
generosity of the resource person. Ma'am told that she would be very delighted when some question in a related area is asked to her. So
Yes.
this is the flavor of this type of exchange program, and I will request other participants to confine themselves to the area on which ma'am focused. Is there any doubt or any other thing you want to ask from ma'am? You can ask.
Yes, Sheila.
Madam, I have a question.
Yes.
Good
Please
evening,
introduce yourself.
Ma'am, I am Swarnali Mukherjee. I am working as assistant professor in George College of Management and Science. Ma'am, I would like to conduct a study on COVID-19 knowledge, assessment of knowledge, attitude and practice towards COVID-19 among the population of Kolkata. So my question is, after collecting data, what statistical tool will be appropriate to me, regression or chi-square? Because here I want to know how much knowledge is associated with education, or how much knowledge is associated with income, or I want to establish relationship between the demographic profile and knowledge level.
See, chi-square had many use, but chi-square is basically used when you would like to see the difference in the mean of, say, different groups, and you haven't discussed anything, you haven't mentioned anything in the groups, right? So here I think that the topic which you are trying to explain is subject to multivariate kind of an exercise, where you want to explain the incidence or the prevalence of the COVID-19 with many factors, including the awareness, understanding, education, and so many things. So I guess that you can start with the regressions. Chi-square, how you will be applying, you are not clear. So if you can tell that this is the point where I can use chi-square, I can tell you that whether it is relevant or not. Because chi-square, you can't just use. How you will use chi-square? What will be your, see, when you use some test, it is basically you are doing some hypothesis testing. So what is your hypothesis? That you have to explain to me, and then I'll be able to tell you that whether it is a right approach or not.
Ma'am,
so
if
I'm not clear, huh?
Okay, ma'am, if my hypothesis is there is no association between knowledge level and education.
Just 1 minute. Hello, I'm in a talk. I'll just call you after half an hour. Okay. Okay. Yes, tell me.
Ma'am, if my null hypothesis is there is no association between knowledge level and education, and my alternative hypothesis, there is an association between knowledge level and education.
So that means here you are trying to see that your H naught is beta naught. Suppose your knowledge level is one variable, and what else you are saying?
Education.
Education. Knowledge level and education are your two explanatory variable, right? And you are saying that beta naught is equal to 0, beta 1 is equal to 0, beta 2 is equal to 0. So it's basically an F test. So and it is better to do it through regression.
Okay. Thank you.
Okay. Okay.
Okay. Thank you.
Yes. So any other questions? Any other questions? So, um, is there any question?
Ma'am, I have one question if you permit.
Yeah, sure.
Suppose I have done multiple regression in the form of factor analysis, whether it is exploratory or confirmatory. Suppose it is exploratory. After that, certain factors are coming out. Could I regress on those factors and get the new result?
Can you please repeat once again? I couldn't follow.
Actually, let me say that first of all, I have done multivariate analysis. There are 60, 70 variables, and I have done multivariate analysis. In specific, it is exploratory factor analysis.
Okay, so you have done factor analysis and you have constructed some index, right?
Yes. And this is statistical construct, but I want to get a confirmatory relationship between these regressed factors, and factors are saved as variables.
So that means your dependent variable will be the index which you have generated through your factor analysis, right?
Exactly, ma'am.
And
so
you
my
want to
question
replace it through many explanatory variables.
Yes, ma'am. Now I want to reduce these number of explanatory variables, as well as I want to develop the causal relationship between all these explanatory variables in the form of co-integration. So it is possible. Is it possible?
No. Actually, what you are saying, what I understood, when you are doing factor analysis, that means you are trying to study something which is multidimensional. Like poverty. Poverty is multidimensional. The poverty affects the education, health, poverty at the social status, apart from the economic deprivation. So poverty is, given that it's multidimensional, you are trying to reduce the many dimensions into a single number, and therefore you are doing factor analysis. Okay.
Exactly.
So when you are doing factor analysis, you will be generating an index value for the through the compression of the data. Now, when after that you are trying to understand that index is dependent on many other factors apart from those which you have already taken. So in that case, and co-integrations is basically used when you have a time element. So here I don't see that there is much scope of using co-integration. It's more of a cross-sectional, or you may take it as a panel data. I don't know whether you have a longitudinal data or not. But I don't think that why you will be using co-integration here.
Thank you, ma'am. Thank you so much. I got my answer. So any other question?
Any other question?
So I think there is no other question.
No other question. Yeah.
Ma'am is talking for more than 2 hours, and I requested her many times that please take water, but I was not audible for some reason, because I was on the way. Anyway, this is the hard work done by a resource person, and wholeheartedly 400%, 500% resources are being exerted by this kind of very humble resource persons like Professor Indrani Rai Chaudhuri. So, ma'am, we are humbled, and we express our heartfelt regards and gratitude on behalf of Indian Academic Researchers Association and Brainware University to your kind
self. I'm really humbled. Thank you so much. Thank you.
Thank you, ma'am. And we expect this sort of cooperation from you again in different kinds of workshops. So thank you so much, ma'am. And with this, I officially declare this technical session for.
Thanks a lot.
Yes. Thank you, ma'am. Thank you so much. And we officially declare this technical session 4 as officially wind up. We'll meet next day, tomorrow. Good night, everyone.
Yes.
Good night, ma'am.
Wish you all the best.
Thank you so much.
Stay safe.
Please all stay safe and stay at home.
Yes, that
and
is
to learn.
that is the only thing which we can wish to each other at this stage. It's very
Exactly,
bad
ma'am.
everywhere.
Exactly, ma'am. Exactly. So this is for you also, and we pray to Almighty for your
Yeah, yeah.
safe and good health, so that we can learn more and more from
Yeah,
you.
same to all you as well as all the participants here. So my heartfelt prayers for all your safeties and securities. Stay healthy.
Thank
Thank
you so
you.
much. Thank you all, and good